Hello everyone, I am MD Mushfiqur Rahman. I'm from Purdue University, and today I will discuss our work on deep causal generative models. So I will discuss mainly first some motivation of causal inference, then I'll try to define structural causal models, and what will be the deep version of a structural causal models. That's like deep causal generative models. First, without confounders, then modular deep causal generative models, which is fork with confounders, and some applications in trustworthy AI. So, in many real-world applications, there might exist confounders or spurious correlations in our data that gives us wrong predictions. For example, suppose we want to know if expensive education if we need expensive education to obtain high income at age 30. So if we look at a data set, we see a positive correlation, and we conclude, yes, we need expensive education for high income. But it might also be possible that the data collected from the individuals had high parents' income. So like their rich parents send them to get high expensive education, and also give them like the seed money to start like business, and their income was high for that reason. And there's like some in some applications also where we might have bias in our data, and that affects our model accuracy when deployed in a test domain. For example, if we train a model, pneumonia diagnosis model, with data from a specific hospital location, and we uh, we want to deploy the model to another domain, then the model might drop its performance, that the model accuracy might drop because the model was trained on a specific hospital location data. So this both of these scenarios says that like we need to understand the causal relationship of the features. If we don't understand the causal relationships among the features properly, then such spurious correlation might propagate to like output of large generative models as well. For example, if you ask image generative model to generate images where a black African doctor is treating white children, you might not get what you expected because the model is trained on data set where you have some spurious correlation exist. So that's why we need to understand the causal relationships among different features. So causal inference can help us to deal with these spurious correlations systematically. So let's dive deep into this. So our question is, does going to expensive college have any causal effect on income at age 30? So we have a data set. We have one column that represents like going to expensive college, and one column represents income at age 30, greater than 50K. So we see a positive correlation, and we say, okay, yes, going to expensive college has causal effect or causal relationship on income at age 30. However, now we have a new we have a new attribute. Suppose we we come to know a new attribute, that's parents' income. That it might also be possible that the parent income is responsible for such correlations. That means when going to expensive college doesn't have any causal effect of income at age 30, but parents' income is actually the relationship that's responsible for such correlationship. But maybe in reality it's actually like both, right? So we want to actually know, okay, what is the specific causal effect of the some value, probability value of this income at age 30 when someone goes to expensive college. So that's like we want to know the causal effect of going to expensive college on income age 30. So if we can like magically remove all this contribution of other variables on this going to college attribute, and fix a value for this attribute, and then observe, okay, what happens to this income at age 30? Did it has its probability distribution increased or decreased? Or like that the income increased or decreased? That's like we're performing an intervention. Then that would actually, and if we see it has increased, then we would say yes, or changing, we would say yes, it has some causal contribution on this. So more specifically, X is said to cause Y if intervening on X changes the distribution of Y. Here X is going to college, Y is income age at age 30. So we don't have a magical way, but in some specific scenario, what we can do is conduct a randomized experiment. That is, and when we perform a randomized experiment, this age, this contribution will be like removed. This age will be deleted. How? So we like force half of the we create a control group. We force half of the people to go to expensive college, and we force another half of the people to go to not go to expensive college. And then after maybe some year or something, we compare income of both group, and then we understand, okay, yes, we're going to expensive college has this much causal effect on income at 30. But this is obviously unrealistic or expensive. Can we use causal inference to do anything? So causal inference actually models any environment or any system with a structural causal model. That is it represents the underlying causal mechanism with some observed variables and some exogenous variables that we don't observe, unobserved, or noise, and some structural functions if that actually represents how each variable is generated from its parents and some exogenous noise. And there's some observational distribution PE of these observed variables. So these structural functions can be represented with a causal graph where the nodes, the random variables are the nodes, and this parent-child relationship in these structural functions can be represented with edges in the causal graph. Now, intervention means we fix a value to a variable x4 equals to 1, and then we observe the value for other variables. So here x4 equals to, after x4 equals to 1, we can see that x5 is a descendant of x4. So x5, this distribution of x5 will change, but x1, x2, or x3 are not descendant of x4. And as a result, if I fix a value to x4 equals to 1, their distribution will not change. So this x4 doesn't have a causal relationship on x1, x2, or x3, but on x5. So obviously, this is the unknown ground truth. We don't observe this. We have to observe this with this observational distribution generated from this ground truth structural causal model. So our goal is to, using this observational data set as training data and using this causal graph as some structural assumption, we want to learn the true structural causal model. So this is challenging because we never know this EI, the environment variables, and thus we can never know these structural functions properly. So what we can do is we can get an approximate version of the structural causal functions f hat I. And if we can now learn the structural causal functions, we can perform an intervention and predict the causal effect. So what is the value of x5 when intervene on x4 equals to 1? So we can actually perform such intervention when we have learned these causal structural functions. So existing deep causal generative models, almost all of them depend on this identifiability theorem, where it's basically saying on a high level that if we have the true SEM M star, but we approximate some other SEM M1 hat and M2 hat. So this is the SEM space, but we don't approximate the true SEM, but somewhere near the true SEM. But all of these three SEM has the same causal graph, and all of the same SEM has the same observational distributions. We can ensure that because we can use these observational distribution data as training data and learn the learn the approximate SCM. So if these two restrictions are enforced, then even if we don't have the true SCM, but we will have the same causal effect as the true SCM. That is, we'll have the same value for the y given to x as the true SCM for the queries that are identifiable, for the queries that are function of this observational distribution. So for low dimensional variables, when we have low dimensional variables in the causal graph, we can estimate the causal effect y given to x with some manipulation of the conditional distributions, observational distributions. because as we seen, like here we can estimate the causal effect from the like some function of the observational distributions. So we with some formula we can estimate the causal effect. This includes also like backdoor adjustment or front-door adjustment. However, when you have like high dimensional variables in a causal graph, for example, some X-ray image or brain MRI or some other variables, images in the causal graph, it's challenging to learn the SCM for the high dimensional causal effect. So then we propose the deep causal generative model, DCM, for this purpose. So the key idea is like a structural causal model sequentially generates data in the causal order. And each structural equation has some observed variables and some unobserved variables. We can mimic these structural functions or this process using neural networks. So here, the structural equations are unknown, but those can be represented in the causal graph. That is okay. This is the parent. This is the parent. So these are like what's that called? Like qualitative relations. That's okay. This is the X is the parent of Z. We don't know what is the function of Z. What is the function Z is using to generate based on the value of X and Y. We just know that they're the parent-child relationships. And we have a data observational data from this SCM. And what we do is we use neural network for each of these functions. We arrange them according to the causal graph. We generate the values of these variables according to the neural networks. That is, like suppose we generate X with F prime X, where the true is Fx. We are using a neural network F prime Y to generate Y and F prime Z to generate Z. So these are unknown initially because we haven't trained them yet. So we generate fake samples from these neural networks, and we have real data. So we have like two distribution P of X, Y, Z. That is the true distribution. And we have Q of X, Y, Z. That's the like distribution implied by the neural causal model or deep causal model. And now we can compare these two to learn these functions F prime X, F, Y, and F, Z, such that these two matches. So for that, how we can ensure that? What we do is like we use a like GAN training to feed the observational distribution. That is like we generate samples from this deep causal generative model. We have fake X, Y, and Z. We have real X, Y, Z feed into a discriminator, and it will give you a loss function that based on that loss function we can update these neural networks. So this is the like main idea of deep causal generative models. I'll go forward, but does anyone have any question before that? Okay, I'll move forward. So here one major assumption is the causal graph is fully specified, and there's no latent confounders or unobserved shared parents between variables. But what if we have confounders? So then comes modular learning of deep causal generative models for high dimensional causal inference. That's modular DCM. So to understand why confounder actually plays a critical role, let's focus on this setup that we previously mentioned. Suppose we have like 30,000 patient data, where we have like COVID symptom for each patient, their chest X-ray images, pneumonia diagnosis, and our goal is to know how likely an average person is to be diagnosed with pneumonia if they have COVID symptoms. That is, predict the causal effect of COVID symptoms on pneumonia diagnosis. So possible situation might be okay. Since we have like both features, let's just predict the conditional distribution probability of n given c, right? Or probability since we have the X-ray images, like let's utilize that. That is probability of first generate probability of X-ray given c COVID, and then predict pneumonia from these X-rays. But if we say focus on the part that is okay, this data set is actually collected from 51 countries, and that is unobserved for each patients, then then there's a problem, because this hospital location will be a confounder for this our setup then, because like suppose socioeconomic health condition in a specific hospital location might affect both the likelihood of getting a COVID and also the like local health care quality of local health care for pneumonia diagnosis. So this distribution of their distribution will change based on the hospital location. So now we are wondering, okay, is our prediction biased, or now like can we trust our model anymore, right? So what we want to do is like instead of using the conditional distribution for prediction, we want to use the causal effect for prediction, right? So that means like we have to perform a causal intervention here and then get the pneumonia, right, in given 2C. But here is a like chest X, let's say high dimensional variable. So how do you do that? So let's focus this here. So this is the like causal graph, and this is suppose the true structural functions. That is like how FC determines how COVID symptom will be generated from its parents, like hospital location and some exogenous noise. FX represents how chest X-ray images are generated from COVID symptoms and some exogenous noise. And pneumonia diagnosis represents FN represents how pneumonia diagnosis is generated. Now, how can we learn the unknown structural functions for high dimensional variables? So as we have guessed, like as we discussed earlier, we use a neural network GC to represent the generation mechanism of COVID FC, which gets some Gaussian noise as input and use CN, some other Gaussian noise as input, which represents these unobserved confounders. Then we have a convolution neural network GX that represents the X-ray mechanism, generation mechanism of X-ray, which takes the COVID as input and some Gaussian noise as input and outputs the X-ray image. And finally, we have a classifier GN that takes this X-ray image and some Gaussian noise and outputs pneumonia, which plays the role of this FN, true FN. So what we done earlier, that is like we have some real data from the SCM and we have some fake data from this like deep causal generative model. So we have to match probability of C X-ray comma N and probability of C Q C X-ray N. So we need to match this. But you see like these are like a combination of low and high dimensional variables because COVID symptom pneumonia, these are like low dimensional variables. X is an image. So this is a complicated distribution we have to match. So it becomes a really high, it's complicated for to match for discriminators, and eventually it sometimes matches just the X-ray images, probability of X and Q of X-ray. So it just trains this convolutional neural network and ignores the other model. For that purpose, we actually need to, if we, so we need to train all the models such as the joint distribution matches. So for that purpose, we propose modular training based on C component factorization. That is like confounded CN. That means like the variables that are in the same C component affected by the confounders, we will train them together. And that's variable outside the C component, we'll train them separately. For example, here, like X is outside the C component, C and N. So we will first train GX, this convolutional neural network. Then we will train GC and GN separately. So let's first feed the COVID values as input, some Gaussian noise, train this convolutional neural network. We're done, freeze it, and now train GC and GN while using GS for inference only, and then just match the joint distribution for like GC and GN, specific joint distribution for GC and GN. Now we show now in this way we can actually like we're splitting the loss function into two parts and matching the joint distribution like separately. So we show that this modularization provides better convergence, and also it gives us like the theoretical guarantee of plugging in pre-trained models. That is okay, why we can actually use pre-trained models where it's not okay to use pre-trained models. So if you remember the identifiability theorem, that is like if we can approximate the SCMs based on the same causal graph and match the observational distribution, we'll have the same causal effect. So same applies for here also. That is like since we have matched probability of C, X, and N, we can now perform do COVID equals to 1 by like not using this neural network, but fixing a value for COVID C equals to 1, then ancestral sampling in the architecture and obtain the value for other variables. And this will give us the probability of pneumonia do COVID. So this is eventually says that the optimal generator can be used to sample from any interventional distributions. Okay, now let's talk about some experiments. First, we'll try to show some application on the like fairness application, CelebA image to image translation. We want to assess large generative models for male to female domain translation task. we want to understand if the translation is causal or spurious. And we want to evaluate correlation among different attributes learned by the models. So here we have like some original image I1, and we extract some feature young and male from this original image, and with some changed version of these attributes like young and female, and the original image we change generate an edited image. Now then we extract all set of attributes like hair color, smile, or orange lipstick and everything, all of attributes P1 from this original image and P2 from this edited image. Then we compare P1 and P2 to understand what are the added attributes that were added to the edited image while image translation task. That is probability of A given do male equals to 0. That is what is the causal effect of changing male domain to female domain on the appearance of new attributes. So what we do is like as mentioned earlier, we arrange neural causal networks according to the causal graph and train to match the joint distribution, and when you use P10 model whenever we need, and perform interventional sample intervention, do sex equals to female, and perform ancestral sampling. So these are the edited image generated from the two models. We want to evaluate their spurious correlations they learned. So what is this is we evaluate one model EGSD, that is like for one model EGSD, it added wearing lipstick attribute to 82% of all images, heavy makeup to 70% of all images. These are causal attributes, so these are okay, this makes sense. But it also adds attractive attribute like increasing the brightness or something to 37% of all images, and young attribute to 25% of all images. So what we did is we changed the image, edited the image, or translated the image from male domain to female domain, but this model changed the attractive attribute or young attribute during the translation. So it should not be the case because like these attributes doesn't depend on the sex. So despite that, this model performs such translation because this types of correlation was present in the data, and this model learned or picked up such spurious correlationships. So this actually, this is a interesting way or cool way to evaluate the spurious if you have any spurious correlation in your learned model. So next, focus on another application, invariant prediction by modular DCM. So in the CelebA dataset, if you see like men are more likely to wear eyeglass, the correlation coefficient is like 0.47. So that means like there's some confounding variable or spurious correlation between sex and eyeglass. So if we train a classifier on this data, the classifier might consider facial feature of a male as an indicator for eyeglass, because it will both look at the eyeglass and also the facial feature of a man, and it will get a high accuracy because there's a high correlation in the training data set. But if you change the distribution of this if you deploy the model into a test domain where you have more female wearing eyeglass, then the accuracy drops to 0.81, 98% to 81%. So it represents the model learned picked up the spurious correlationships. So how we can get rid of that? The goal is to train a classifier that's invariant to distribution shifts. So now the idea is that is we know this in this causal graph, do sex equals to 0 or sex equals to 1 will remove the spurious correlation between these attributes, right? So what if we generate an interventional samples from after performing an intervention, and then train a classifier on that interventional dataset? So for that purpose, we need to generate this high dimensional interventional dataset, right? So we can actually use modular DCM for that purpose and use a train invariant classifier on that dataset. For that, what we do is okay, so the classifier one, that's the classical classifier, it's just training on the use the training dataset to learn the classification. And what we do is we generate this eyeglass and image dataset from probability of eyeglass image do sex. For that purpose, step 1 is to we first use neural networks, train the neural networks for sex and eyeglass together. And then since image is outside their C component, we can use a pretend model GI. We use like interface GAN for this purpose. And now we plug them according to the causal graph, and then we intervene on 6 equals to 0 or 1 to uniformly to generate corresponding images or the interventional data set. Now we merge this interventional data set to the original training data set and get an augmented data set so that we can get the best of both worlds. So here, classifier 1 that was trained on the training data set. It obviously has some male eyeglass bias, so it has accuracy on this like 6 equals to 0, eyeglass equals to 1 group, right? But when our augmented data set, we train our classifier on after merging both different varieties of eyeglass images for both sex and both male and female from in this interventional data set will enforce the classifier to focus on only the eyeglass property. Since now we have both male and female equal amount wearing eyeglasses in the data set, the classifier will not focus on any male feature. It will just focus on the eyeglass feature, right? And it will have, like, if you see, if its accuracy improved from 0.81 to 0.9 in the test domain. So this is also an interesting application of causal generative models. So what we learned, the summary is like we first discussed how we can model any environment with structural causal models, and then when you have high dimensional variables, we can use neural networks to mimic the structural causal model as deep causal generative model. Then when you have like confounders, we can use this modular, we can utilize the modularity, C component based modularity to train the deep causal generative models and sample from the interventional distributions. And finally, we can do some like cool application like invariant prediction or spurious correlations from this using these approaches. So the takeaway is like utilize the causal relationships of your features to get the like robust prediction or get fairness. Yeah, thank you.